Hello everyone, I am Dr. Raviraj. Today we are here to discuss about a very famous additive manufacturing approach that is known as directed energy deposition, and we are basically focusing on a trademark of this DED technique, that is coaxial wire laser based additive manufacturing approach. Before moving to the DED approach, very first we would like to discuss general perspective of additive manufacturing technique. What is additive manufacturing is all about. So in brief, if we say it's unlike conventional subtractive manufacturing technique, rather it's a additive manufacturing which can fabricate any component by depositing feedstock material, whether in the form of wire or powder, when it interacts with the energy source, whether it is laser or electron beam or electric arc, and when it interacts with the energy source, it is melted and deposited on the substrate layer by layer, uh, and build the component with the desired geometry, and which is governed by a digitally defined heat source trajectory. So this is general perspective, general definition of, you can say, the additive manufacturing. So what are the major applications? So it is of course it is widely used in aerospace sector, energy sector, biomedical sector, automotive, and yeah, product development is highly utilized sector. So these are some advantages. So out of which the major one is like we can build a component in a single go uh, to fabricate a very complex geometry, which is of course not possible with the conventional approach. And due to that, just because we are producing a very complex geometry directly, so it eliminated the any specific kind of post processing approach. So due to that, the material wastage is also reduced a lot. And due to this, the carbon footprint is reduced a lot, so that we can say it's a greener approach. And of course it's also we can say additive manufacturing is a portable manufacturing approach. For example, if you wanted to build suppose a building structure, so we directly can set up the associated manufacturing tools together to build a component in a particular location. So in that way we can say it's highly portable. Along with the advantages, there are several disadvantages too. If we are not interested for just because it focuses on the specific kind of production. So for that point of view, if we are looking for the bulk production, so initial cost is too much high, and the production cost is also very high if we are going to produce a mass production. If like production volume is very high and the complexity is very high, in that case the production cost will like shoot it up. So that is one of the disadvantages too. And of course the material availability for this AM technique is very limited for with us. And speed, if we are fabricating any of the component in a bulk production, so speed is significantly reduced. So that is also a disadvantage if we are going for mass production. And in many of the additive manufacturing approach, we surely need some of the post processing to increase the surface roughness and the surface waviness and all those kinds of defects. So that is sometimes also considered as a disadvantage. So now why additive manufacturing is needed? So there are two reasons, if I say. So first reason is like if the production volume is not very high, production volume is very limited. So in that cases, if we are producing any component with the conventional approach, the production cost is very high. So if we look into this particular graph, we can see if the production volume is very less, then additive manufacturing is the technique which is preferable to produce. And another is like if the product complexity is too high, so in that particular case also the production cost is increased significantly. So in that kind of manufacturing, the additive manufacturing played a vital role to reduce the production cost. Due to these two regions, we can see here the several very complex component belongs to the different sectors, which is difficult to produce by the conventional approach, which is of course very easily can produce by the additive manufacturing. So if we talk about the types of additive manufacturing approach, so here we can see there are several kinds of additive manufacturing technique, but just because we are focusing on the metal and alloy based additive manufacturing approach, so basically two is the key manufacturing approach, that is powder bed fusion technique, and the second one is the directed energy deposition technique. If we talk about the material which is available for the additive manufacturing technique, so there are there is a range of material which can be used, uh, just like nickel based superalloys or iron based alloys, copper based alloy, aluminum based alloy. So there are several materials we can use, but of course all these materials is used different with respect differently with respect to the different kinds of production technique. So because we are focusing on the aerospace sector, I'm mostly focusing on the aerospace sector. So I can say, due to of the COVID-19 pandemic scenarios, the after the 2019, there is a significant drop in the aerospace sector requirements. That is about the 15% or so, just because of the air travel restrictions and the social distancing protocols. But once this uh, protocols once these restrictions is lifted off, so due to that we are expected that up to the 2025 this demands reached suited up to the 430 billion US dollar or more than that even, just because to increase in demand in the field of aerospace civil aviation sector, or increase global military expenditures, or high market activities in space sectors. And the of course the due to that the substantial research and development project fundings is 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 attracted. So we can say there is a huge scope in the field aerospace sector, and just because of the booming for funding, uh, this technique is very much favorable to do area of production. uh, Here we can see the material which is like uh, used in the additive manufacturing approach. So we can see here, so conventionally this is very less used, but after the 2010, the utilization of materials with the additive manufacturing is rapidly increasing. And in this also, the titanium alloy is like mostly used as a material for fabricating any of the component. And of course the titanium is having very significant property of lightweight and high strength. That's why it's used in the aerospace sector. And along with that, also in the biomedical implants also titanium alloy is used. Just because of that, this steel and titanium alloy is basically used a lot. Along with that, also like nickel based alloy or ceramic or composite or magnesium aluminum based alloys is also used in this. Now, what are the current objective of additive manufacturing? So just because it's few decades old technique now, so but what are the current objective? The current objective is basically based on the technical and economical perspective. So it's like functional performance and the lead time reduction in the production units, production line, and the to lightweighting the components of the sectors, different sectors like aerospace, and the just to we can directly produce a very complex geometry. So complexity is also a very highly demanding objective, and just because of that the cost is reduced, and yeah, of course the production technique which can safely and produce the critical components, so the certification is easily can be obtained. So additive manufacturing is also fulfill that kind of requirements. And of course this is a sustainable approach. So all these factors are like very much interrelated to each other. So these are the current objectives to manufacturing. Now we are focusing on the directed energy deposition technique, that is an additive manufacturing. So if I give you the orientation about this, what exactly the DED is. So with the schematic, if we looks here, so we can see energy source in the form of laser is coming in a optic axis of the laser axis. It's coming like this, and along with that, from which nozzle it's coming out. From the same nozzle, the material in the form of powder is also coming, and the laser heat source is interacting with the feedstock material powder, and it's melted together. And when this whole nozzle is moving in particular direction, in that direction deposition is like we are found in the deposition. So in that way, layer by layer, and we can get the product. To build the product in the like uh, jet direction, you can say, or in the upward direction, we build the component. So if we are looking in more detail, so as we see, so this is the laser beam is suppose moving in this particular direction of the arrow. So what is happening, the this laser beam is basically interacting with the feedstock powder material, and when it's interacted, so due to of the energy generation, this metallic powder is basically melt, and when it is melted, so it is like deposited on previously made or base material, deposited on that material, and in that way we are getting some specific height of the deposited layer, and in that way we are forming a laser deposition. And once this particular layer is over, we can move the nozzle in some jet direction, in plus jet direction, and we can above, and we can deposit the melted layer again on the previously deposited layer. In that way we can move a plus jet direction, and we can build the component in height. So this is the basic principle. And if we talk about the is the subclassification of the DED technique, this is basically classified in two way. So the first way is like based on the energy source, what we are using energy source. So the first energy source is like the laser, and another one is like electric arc or plasma, and the third one is like electric beam. And if we talk about this, it is also classified based on the material, which kind of material we are using. So it's two different kinds of material we are used, different form of material we are using, like powder or in the form of, so bulk material in the form of wire. Again, the wire is also like feeding in two way. One is at the angular direction, with respect to the beam optic axis, and another one is like we are feeding the wire coaxially in the optic axis of the laser. So again, this is again in classified in two way. So now, what are the very essential things which is which we are like talking about the DED. So it is also sometimes known as the, if we talk about the coaxial wire laser additive manufacturing approach, it's also known as sometimes the laser metal wire deposition technique or laser wire based DED technique. So this technique is basically based on the laser welding, and the wire filler material. This technique is very much sensitive to the laser wire interaction, where the laser like interacting and melt the material matter, that is wire, and deposit it. So laser wire interaction is very much important. So so this is very means important point. Along with that, there are the critical parameter. What are the critical parameters we take? So in case of CW lamp is three major parameter, like laser power or the scan or traverse speed, and third one is like wire feed rate. What we are what how fast or how slow the wire is feeding. So this is three critical parameters which we are varying. Along with that, there are some additional parameters also which we are taking care, like laser wire or laser wire or the laser substrate angle, in which angle the laser and wire is like oriented to each other. Another one is like wire tip position, with respect to the melt pool. Yeah, of course, when wire is feeding and laser is also like coming, so at which particular distance from the nozzle it's interacting with the energy source and melt. So that is also very critical to control, critical bed which needs control. Along with that, wire protrusion, distance, and the feed direction, in which direction we are moving. Suppose if we are, of course, if we are using the coaxial wire-based laser direct manufacturing technique, so we have some freedom to move in any of the X, Y, or G direction. But if we are talking about the lateral feeding of the wire, so of course we need to take care about the inverse direction we are moving. So that is also a parameter which we need to take care. So like, okay, of course, when material is interacting with the matter, laser is interacting with the wire. So which kind of deposition we are getting? So basically, we are getting three different kinds of deposition. Uh, First, if we talk about the deposition type, so it is like globular deposition or globular transfer. So what is exactly this? Suppose when either wire is feeding very quickly or laser power is too high, so in that way the unstable melting is there, like too much melting or too fast melting is there. Just because of that, we are getting like a globular shape of the deposition, which is like not we can say preferable if we are made the whole part. Just because of the globular transfer, the component either fabricated uh, fabricated very roughly, or some waviness we are found in the final deposition deposited component. On the contrary, if we talk about the plunging transfer, it's all about when suppose wire feed is very less or the energy power is very less to melt the material. So in that way, we are of course not getting again the stable deposition. In that case, we are getting unmelted or a non-uniform deposition. So this is opposite of the globular transfer. But when we are balancing these two, so we are getting the smooth deposition or smooth transfer, which is like preferable. It's a balance of the energy and feeding and another parameter through which we can get a very uh, stable deposition. So of course, we are also like installing the feedback system, like we are giving input to the machine, but exactly machine is working according to that or not. For confirming that, we need to install some feedback system. So those feedback system in the form of like CMOS camera or the IR camera, along with that some pyrometers and all those feedback system we are installing to know the exact deposition, what kind of deposition is going. So there are several advantages with the DED technique. Is like we can use the okay, DED technique is basically used for the metal based deposition mostly, because we are discussing here about the metal and alloys. So uh, the the advantage is like over, we are comparing it with the another AM technique which is used for the metal and alloys, that is powder bed fusion technique. So compared to that, if we say it has a big advantage of, because we are using the bulk material also. So we have a freedom of a range of material which we can use. Processing of material, like processing of multi material, we can, like, of course we can add one material, and along with that we can add another metals or alloys wire to make the component of the multi material. So so in that way, composite we can produce or functionally great material we can produce. So this is one of the advantages. And next advantage is like high deposition rate. By DED we can get a very high deposition rate, like 10 kg per hour is we can, what we can achieve. It's basically boost the production uh, reduce the production time. And we can also produce a very big size of component by using this uh, with the exact geometry what we wanted to produce. That is generally known as the near net step fabrication. We can also use it for repairing and coating. So that is one of the advantages. There are some other advantages also, you can see directly here. Along with the advantages, there are several disadvantages too, like just because we are melting the bulk material, so just because of this phenomena we are giving a lot of energy which increases the temperature a lot. And just because of this melting, and when nozzle is moved ahead, then the previous deposition is basically cooled down immediately. Due to that, a very quick temperature variation there. Due to that, the thermal distortion we can see. Along with that, the residual stresses also we can found in the deposited layer. So this is one of the disadvantage. Along with that also, just because the we are depositing material at high deposition rate, due to that we can get a very low dimensional resolution. And along with that, surface waviness or surface roughness we are like obtaining in this technique. Okay, higher surface roughness. Yeah, of course, the higher surface roughness we are getting just because of that. And the complexity limit. Yeah. So if you talk about the complexity limit, because we are feeding the material in from one particular direction, and laser head is also moving in X and Y direction. Just because of that, X, Y, and Z direction movement only is possible. So it limits the complexity what we are expecting. Uh, if suppose we are getting some rotational degree of freedom also, so we can get some more complex, we can produce some more complex component. But just because of the limited degree of freedom, we are restricted with the complexity too. Post machining is also required just because of the low resolution of the surface and low powder recyclability, because we are inputting too much amount of energy. Just because of that, the powder is like um, uh, not remaining for the next use, or recycling is also very difficult for this kind of applications. So now what are the applications? So as we discussed, because of its capability, we can produce a very big size of component and multi-material component or functional graded material. We can produce the component. So in that way, we can produce a component like aerospace component is like rocket nozzle liners with the integrated feature. Internal feature is like is very complex. So we can produce this kind of component by this technique. And the next one is like manufacturing large parts. Of course, with high deposition rate and high manufacturing speed, we can produce a larger component. and repairing and coating. Yeah, of course, suppose if we produce the impeller with the conventional approach, and due to of the application, some cracks or some kind of defects is generated on the sample, which is very local, which is very local. That kind of defects we can repair by using the DED approach. And of course, coating, if we talk about, so mm, conventionally it is very difficult to achieve a very complex kind of coating. For example, if we talk about the titanium component is coated with the tantalum. So tantalum's melting point is very high. For example, its melting point is 3000 degree centigrade. So it is very difficult to coat it with the conventional approach. With this kind of approach, we can very easily melt the tantalum localized because of localized melting, and we can coat it on the titanium component. In that way, we can achieve the tantalum coating on titanium very nicely. So the similar way we can coat the calcium phosphate on the titanium component, or high temperature copper on the Inconel 718 kind of alloys. So this can be achieved by this DED technique. So these are several applications of this DED technique. So now, what are the parameters is required for the DED technique? So three category of parameters which we are getting, which we are focusing. First one is the energy source what we are using. The parameter related to that, that is uh, like what are the laser power we are using, the laser wavelength what we are using, the laser spot size what we are using, what kind of laser we are using. Those things can be controlled by this. Second one is like feedstock material, which powder or wire or what kind of material we are using, the property and porosity and so many parameters associated to that is also like we can control. And the deposition variable, for example, the what laser power we are using, what hatch spacing we are using, what scan speed, what feed rate we are using. Those can be like uh, is very important for the. So these are the several examples of the which can be produced by the DD technique. Here you can see rocket nozzle, you can see, and impeller. The whole impeller is manufactured by this technique. Along with that, the body of this kind of jet engine we can achieve, and the pipe joints which are directly produced by this technique. So these are some very interesting example which nowadays is fabricated with the help of this DD technique. So these are some